want to thank the organizers for inviting me to such wonderful conference. The subject of my talk is severe symplectic geometry. And I plan to talk to explain some results which are not they are not very new, but hopefully new for some. So, in principle, zero symplectic. One can say that the subject studies continuous analogues of symplectic objects. So, so continuous of objects from symplectic geometry. And we'll mostly focus on one object, which are symplectic homeomorphisms. But first, it's not. I'm not sure when this began to be studied, but probably it started with the Poincaré-Birkhoff theorem, which appeared in Poincaré's study of celestial mechanics, and in this theorem states that if we have an annulus on the plane and a closed annulus and a homeomorphism which rotates the boundary components in opposite directions, then it must have at least two fixed points.
Area preserving.
Sorry, of course, thank you. So area preserving, it's very important, and also this twist condition also important. And later on, I will come back to this, but maybe main motivation for recent development related to the subject is motivated by, so motivation comes from the celebrated Eliashberg-Gromov theorem. It states that the following, so if we have a symplectic manifold and a sequence of symplectic diffeomorphisms, which C0 converge to phi, which is itself a diffeomorphism, then phi in fact is preserved symplectic form. So this, so the condition for being symplectic map is defined using derivatives, and here we have uniform convergence, but still we have this rigidity result, which appears to be surprising, and this theorem motivates the definition that I will mostly talk about. So this is definition of symplectic homeomorphism. So so phi. So another way to say it that if we consider Okay, so what is symplectic homeomorphism? So symplectic homeomorphism, and I will denote the set of symplectic homeomorphism by sim bar, are just homeomorphisms which are uniform limits of a sequence of symplectic diffeomorphisms. So it's closure of the symplectic group in the group of in the group of homeomorphisms. So phi in sim bar if there exists a sequence of symplectic diffeomorphisms such that phi k C0. Okay, if phi is homeomorphism, and it is the zero limit of a sequence of symplectic diffeomorphisms. And the one should also add convergence on inverses if M is not compact, or it depends which category we work, if they're compactly supported, and so on. So one can reformulate this theorem just by saying that if we have a symplectic homeomorphism which is smooth, which is a diffeomorphism, then it must be symplectic diffeomorphism. And now one can try to understand better.
Is it clear or unclear that this is a local property? So like if you have no?
Only in dimension 2. So yeah, so there are different definitions. One can say it's a homeomorphism such that locally it is the zero limit. And the problem in all this subject is that most basic fact about the diffeomorphism and homeomorphism is not clear, which is the fragmentation theorem. So fragmentation property that says if we have a covering of our manifold by open sets, and we have some, in fact, we can ask this only for symplectic diffeomorphisms, that we have a symplectic diffeomorphism which is zero small, and we express it as a product, as a product of symplectic diffeomorphism, each one supported in its open set, and also they are C0 small. And this is completely unclear in dimension higher than 2. And this is an obstacle for many things are unknown here.
What about for Hamiltonian? Also?
Yes, sorry. Maybe this is bad formulation, because for symplectic diffeomorphism we have the flux, and if we have a small chart, then each one. So better to formulate it for Hamiltonian. So thank you for your remark. It's not really, or if one can formulate it also locally, it doesn't really matter. But also for Hamiltonian, so this the same question is not known.
Sorry,
Okay.
can I ask a question?
Yes.
So you're saying that it's not known that Hamiltonians have fragmentation, even in compactly supported case?
Yes, for dimension greater than 2. So compactly supported meaning, for example, on closed manifolds, or you can have
Okay.
some local statement in this sphere, but this is not completely not clear. And if we knew this, we could have so many statements proven. So basically, recent development tried to avoid all this property that is completely unknown and prove things differently. But let's come back to this definition. And so one can ask, so what, ask question to understand better symplectic homeomorphisms. And for example, one question which is quite vague, but one can still ask, can symplectic homeomorphism do what symplectic diffeomorphism cannot do? Okay, so then you can map smooth submanifold to non-smooth, but let's try to formulate a better question. So, for instance, can do symplectic homeomorphism preserve symplectic and some symplectic invariant, and which invariants are really preserved? And one of the first, maybe the first theorem after in this direction was is of Obstein. So this subject, C0 symplectic geometry, has both rigidity and flexibility sides, and I will try to explain statements from both, but more focus on flexibility. So, so what does this theorem say? So if you have a symplectic manifold, then sigma is a hypersurface, and we assume phi is symplectic, and image of sigma under phi. So we assume, let's assume that it is also a smooth hypersurface. Then phi maps characteristic relation of sigma to the characteristic relation of sigma. So we have characteristic lines, and we must go to characteristics exactly as in the case of smooth maps of symplectic diffeomorphisms. And this statement was later generalized by Vincent Comilliard, Leclerc, and substances indeed. To the case of co-isotropic submanifolds, and in case of co-isotropic, additional statement appears, because so I assume again that M is a symplectic manifold, and we have C in M isotropic, and phi is in symplectic homeomorphism, and its image is smooth. This is a manifold. And C prime. Okay, so in the case of hypersurfaces, we know it's again hypersurface, but in case of codimension greater than 1, it's not a priori clear that we get co-isotropic. So this is first statement that this is co-isotropic. And again, characteristic relation most opportunistic connection. Okay. On C prime. And this statement, in fact, it can be reduced to the case when C is Lagrangian, and so in some sense, so for the Lagrangian, this is can be seen as generalization of Eliashberg-Gromov theorem, because we can consider the graph tree. So this is about rigidity, and this okay, so we have some statement which may be not very surprising, but and one can ask, what about flexibility? Are there some invariants that are not preserved? And one can consider this the same context. So here we consider action of symplectic homeomorphisms on submanifolds, and one can ask more generally. And example of flexibility is appeared later. This is theorem joint and it says that one can construct example of symplectic homeomorphism which does not preserve symplectic area. So this and this example is in dimension 6 or higher, and for example in R6 one can find a symplectic homeomorphism so when we decompose R6 into three complex planes in standard way, then phi x, if we restrict phi on symplectic 2 disk, correspond to the first factor, it shrinks it by 2 for any z in the unit disk. So the basic property of symplectic diffeomorphism, that it preserves symplectic area, does not hold here.
Can this kind of like generate some form? Like it cannot be completely Lagrange.
Yeah, yes, it can.
It can be completely Lagrange? No.
Isotropic.
Isotropic, yes.
Yes, it can. So it's actually the only recent statement that I want to tell. Not only, but one of few. So I will tell it a bit later.
So being isotropic is also not preserved, yeah? Being
Being
isotropic.
isotropic, so okay, I will tell already. You can have a map which takes symplectic disk to isotropic disk, and I think it's nobody checked this, but I believe any disk can be mapped to any disk, so nothing is preserved actually, and this. Of course, this is important that it's dimension 6, and dimension 4 such example does not exist. One can prove also such a rigidity statement. And the main tool for proving this is some version of H principle, which reminds very classical H principle of Gromov, of Eliashberg and Gromov, but there is some additional feature to it. We call this quantitative H principle. I'm not sure this is a very good name, but it somehow stayed from there. So this is a version of the C0 aspects appeared already from the beginning in many H principles, but here, so for example, originally it was considered in case when we have codimension 2 or codimension 4 symplectic submanifolds or subcritical isotropic submanifolds. But what was considered is mostly if talking about C0 property, that something like that embedding can be C0 approximated by embeddings, or some homotopy C0 approximated by symplectic isotopy. But here we need a bit more. We need that that in fact a statement about the whole flow on the ambient space. So the statement, for example, in this particular case, we consider restricted situation when we have two symplectic disks. But it's not enough to consider 6, but say some open set 6, and we assume that we have these plane closed in disk, and we assume that there exists a homotopy between 0 and 1 of size less than epsilon. So size meaning that any point, the trajectory of each point has diameter less than epsilon, small diameter, and then there exists a Hamiltonian flow phi t compactly supported on R6, which maps the first is the second one, and phi t has size less than 2x, a small size. So meaning that trajectory of any point, so we have two disks and we have a small homotopy, and the statement is that one can isotope 0 to 1 with help of a small Hamiltonian flow that not only point on the disk, the trajectory of each point is small, but for any point in the ambient space.
So what are the assumptions on 0 to 1?
Sorry, these are symplectic disks. And this is important. This property about ambient smallness of ambient flow is important for application. So how one can, using this statement,
Here everything smooth.
smooth.
here size is just like supremum distance overall point.
Yeah,
It's not
so
like
this is maximum of diameter of for all. And how can one use this statement to show this result? So we can start. So we can start by the following. Just we know that we can take, for example, the standard disk. And add here, perturb it a little bit, and obtain a disk which has different areas. So pullback of symplectic form is half, and we can find nearby disk and again nearby disk and so on. And we can try to first map the first disk to the second one, the second to the third. And we know that ambient map is C0 small, and we can do, when we compose all of them by this statement, we get some map in the limit. It's not so clear why it is a homeomorphism, because one can have here points that eventually goes into the limiting disk, so it's not, some point may coincide in the limit. And one need to be more careful. So this naive construction doesn't work, but one can do a better, follow a better way and use these H-pins. So this is about okay, and in fact recently we proved with Hofstein that the same statement holds for subcritical isotropic submanifold disks. So it's quantitative H principle. And so this in any dimension, but one can apply the same statement to this strategy, which I did not explain. So some upgrade of this one and obtain this example when a symplectic disk is mapped to isotropic disk. So this is one example of flexibility in C0 symplectic geometry, and another subject that appeared is related to the Arnold conjecture, and here so I can come back to Poincaré-Birkhoff theorem that I mentioned at the beginning, and so it states its theorem about fixed points of area preserving homeomorphisms. And maybe this was one of motivations for Arnold to.
But this theorem was for diffeomorphism, not for homeomorphism.
Right, right. So Arnold considered diffeomorphism. It's much. So it's more convenient.
But Poincaré also considered diffeomorphism.
Yeah, yes, but somehow he arrived to homeomorphisms as Poincaré map, its behavior near boundary is not so clear. But in the interior, so in his case, these are diffeomorphism in the open annals. But it's interesting still that this statement holds for homeomorphisms. So Arnold formulated conjectures which motivated very much symplectic topology, and I will write down that this version that maybe most general, that on a closed manifold, symplectic manifold, we have a Hamiltonian diffeomorphism, then it has many fixed points. Must have fixed points at least as a minimal number of critical points of a smooth function, and denoted by crit n. Minimal of critical point. So in fact, yes, critical points of a smooth function on F. And here also degenerate situations are considered. And so any smooth function, we can consider its time on map, and maybe this was also motivation. But later on, this, in fact, the Poincaré-Birkhoff theorem was generalized, and in fact, it is a theorem of Matsumoto that later was reproved by Lagrangian. That in dimension 2, Arnold conjecture calls also for homeomorphism. So this this theorem is very deep and uses developments in topological dynamics in dimension 2. So this is a theorem of Matsumoto that if we have a closed surface, closed symplectic surface, then Arnold conjecture holds. So what do I mean by this? That we have the same lower bound. We do not consider continuous functions or something like this, but that in the case of the sphere for phi, so if we have phi a Hamiltonian homomorphism, in the case of the sphere, the number phi must have two fixed points. In the case of genus, at least one. High genus, number of fixed points. It's natural to ask if one can generalize this to high dimensions, because we have notion. Okay, we do not yet have notion of Hamiltonian homeomorphism, but one can try to define it in the same way. So let's.
So what is phi again in this theorem?
Phi is a Hamiltonian diffeom. Well, I'm sorry. Yes. So phi. Yes, I'm sorry. This I didn't want to say a statement of Arnold conjecture. So phi is a homeomorphism. Homeomorphism area, and orientation preserving. And one needs additional condition that remains being Hamiltonian. So it has zero rotation vector or zero flag. And this and exactly this kind of homeomorphism appears as zero limit of Hamiltonian diffeomorphisms, and therefore we can try to define bar to be just zero closure. Group of homeomorphisms. And one can ask, so this definition makes sense also in higher dimensions, and one can ask if the same, one can prove some rigidity, but it turns out that there is complete flexibility in this case. In higher dimension, this is theorem with and so familiar and so consistent. And if on any closed symplectic manifold dimension this form, there exists homeomorphism with only one fixed point. And one fixed point is unavoidable because if phi is uniform limit of Hamiltonian sequence of Hamiltonian diffeomorphism, each one of them has a fixed point by Floer theory, and we get in the limits at least one fixed point. This is and one can try to ask, does it finishes the story, and does it end the story, and one can still reformulate a better version of this, but in terms of spectral invariance. But I want to focus.
Can I ask, is there any condition on the Hamiltonian homeomorphisms in terms of Hamiltonian functions converging?
Yes, so I hided something here because so this I consider it quite big, a certain version of this group, because there was also there is another more delicate definition that takes into account also Hamiltonian function. And this in fact it was introduced by Müller, and this definition somehow he gave it to try to solve one of important questions in topological dynamics. At the end it was solved using his approach recently, but this, okay, maybe I explain this, that one can also look, because when we pass to the limit, we have a sequence of Hamiltonian diffeomorphism. It has a limit as a homeomorphism. We completely forget about the Hamiltonian functions. And but one can define the following version, that we, instead of, so we moreover can try to define continuous Hamiltonian flow, that we have a flow phi t, a flow of continuous flow of homeomorphisms. M, and we say that so this is a definition of Miller and Hall. So we say that phi, this flow is generated by a continuous Hamiltonian function h. If h is a continuous function and there exists a sequence of functions on independent functions such that hk uniformly converges to h just as a sequence of functions, and the flow of phi of hk uniformly converges to our flow. And in this case, we have also generating continuous Hamiltonian. And this definition is more restrictive. And in fact, one can construct also phi, which is time-one map of such continuous Hamiltonian. What I want to emphasize that also in our approach to prove this statement, we use a certain also kind of H principle just for curves. And this is much easier statement, but it says that if we have say symplectic manifold of dimension at least 4 and two smooth curves which gamma 0 and gamma 1 which coincide near the ends, and we have some homotopy between them which has small size less than epsilon, and such that the area of disk which we obtain from this homotopy is 0. So they have the same action. Then one can find a Hamiltonian flow also C0 small, which maps time on map sends gamma 0 to gamma 1. And moreover, we need if we want to also construct this more restricted example, we need some kind also to require that the Hofer norm of this flow is small as we want. It also can be achieved. And also this flow is supported in some small neighborhood of this. Okay, so this was about some. So maybe I'll tell a few words how we can use this statement. So the statement is only a small part in this case of the construction. So the construction is starts with choosing some.
So the construction of what? What do you call it?
I want to construct a Hamiltonian homeomorphism with one fixed point. So we start with.
And this is only for your definition. Like for Hammer, it doesn't work.
It does work.
Does work.
Yes, but you need additional. I will not now present the full details now, but just a picture. So we have, let's start with some smooth Hamiltonian function, which is autonomous, which is too small. and also Morse. Let's assume that all critical points are non-degenerate. We have finite number. We consider its time on map. So starting with this H, the first step is to construct. So time on map for us is not good. And we want to construct instead a Hamiltonian homeomorphism, right? Or maybe called psi. Hamiltonian homeomorphism obtains from this time on map by very small perturbation, such that psi admits psi has the same fixed points as phi. Instead, in fact, we perturb phi outside, away from this fixed point, and this psi has an invariant tree. So tree is a union of curves that connect. Okay, in this case, this is a curve, but it can be more complicated, which connect all of the fixed points. And such invariant tree is impossible for Hamiltonian diffeomorphism because if it exists, an action difference between critical points, between fixed points, is zero always. But still, one can use some dynamical idea to start, say, near this fixed point and go with this time on map, call it phi, and then compose with very small Hamiltonian diffeomorphism supported in small neighborhood here to move this point downwards, and we continue this for a very long time until we reach any point near second fixed point, and then so by small C0 perturbations we don't create new fixed points. If we make this perturbation outside of neighborhoods of our initial fixed points, and we can in fact make such perturbation that iterations move point anywhere we want in the manifold, and then we can continue constructing the trajectory such that eventually it make this perturbation smaller and smaller near a chosen fixed point, such that eventually this sequence converges to fixed point. And this way we construct a trajectory, two-sided trajectory, which on one end it converges to one fixed point, on the other end it converges to another fixed point. And the next step is to, so this is still not an invariant curve. And now we connect in a certain way the nearby points and perturb further our map. So we, for example, take this curve, we map it here where it's small perturbation, and then using this quantitative edge principle, we map this curve to our next one, and so on. So this is some iterative procedure, but here the main thing that we make this perturbation without creating new fixed points, and we can do it by the fact that by this quantitative mesh principle, which allows to map one curve to another in such a way that the ambient map is also C0 small if they are C0 close. So maybe I'm close to my time is close to n, but I want maybe now to So this what was done before, but still many questions remain. And I want to formulate two of them. And maybe at least one of them is in the spirit of questions that are being studied right now, but in different contexts. So one question is, so this construction of Hamiltonian homeomorphism, which shrinks symplectic disk, it uses this quantitative edge principle, which really does not care about derivatives. And so the map is C0. We have C0 closed symplectic disk. We can map one to the other, and the ambient map is C0 small, but and also the flow is C0 small, but this is only C0. And this, because of that, we do not know anything about smoothness of these symplectic homeomorphisms. And one can ask how smooth can it be? So if we have symplectic homeomorphism, say of R6, and it does not preserve symplectic area, so let's say it acts the same way. So for example, can one construct maybe not smooth, but Hölder example, or at least what are restrictions of modulus of continuity of such map? So this is one possible question, and another is that completely unclear that this way we can construct a Hamiltonian homeomorphism with one fixed point, but there is another famous conjecture, it's Conley conjecture, which talks about periodic points of Hamiltonian diffeomorphisms. And one can also ask, can we make more degenerate counterexamples? So does there exist at least one example where we have a Hamiltonian homomorphism with only one periodic point, for example? And this approach does not work because when we make these small perturbations, it does not care about iterations, and we can create by these small perturbations many fixed points for the iterations, and this is not clear. So new ideas.
I think I can give you an example for that in
Yes.
If you take a twist map, you just consider the metric or the round metric on S2. Just take the geodesic flow, but don't just take the norm. Hamiltonian is just QP is just P, the norm of P. That's not smooth section. So everything is periodic and is that good?
So can you construct on a closed?
No, I don't know.
Yeah. So if not closed, then
Okay.
yeah. Okay. Maybe we can discuss. But, so the setting that I want to consider are closed manifold where are not conjecture always hold. Yeah, but thank you for.
What's the status of other this kind of initial questions? Okay, so first of all, okay, let's talk about closed manifold. Is S4 symplectic?
I believe that not, but I don't know.
So there's no kind of counterexample of some kind of like to have something like without cohomology, symplectic, or
So this is
or non without almost complex structure, symplectic. Any closed manifold will admit symplectic structure is topological, but like violate some basic.
I believe that if one could have fragmentation lemmas for in dimension 4, for example, then one could try to approach this.
So in dimension 4, probably that's most realistic to prove that it's not, right?
Yes. So maybe the approach of Gromov in his 85 paper, okay, he proved rigidity of symplectic structures on CP2. So can also help to proving fragmentation lemma, but looking at these two foliations by homomorphic curves, but I did not succeed using it. But it seems very promising, but
the kind of in negative direction, maybe in some high dimension, you can prove.
I believe that it's not possible. I have no really evidence for this, but I believe it's not possible.
So like sphere in same dimension should not be symplectic.
This is, I believe, but I cannot give you an argument for this. It's just from general. That if you have a large codimension submanifolds, then you can have flexibility. But if you consider such kind of statement, then probably it's rigid. I don't know. Yes.
So just to clarify that question, so if S4 being symplectic would mean that there exists an atlas where a topological atlas where the transition maps are homeomorphisms, or
Yeah, are symplectic homeomorphisms. So this question appeared many years ago. Yeah, but it's still unclear.
There is this famous question of Arnold about invariance of helicity for volume preserving homeomorphisms of a three-dimensional manifold. So for this, one has to send the volume preserving field to another volume preserving field. So it's kind of the on the transversal, it will be something like a symplectic homeomorphism. It is kind of smooth in one direction, but it might be a homeomorphism. Can you say something with this method? Can you think about that?
I think recently there was a breakthrough in this kind of statement in the rigidity side. There was proof that there was a question if the Calabi homeomorphism can be extended to Hamel, and this is related to for the disks, and this is related for the two disks, and this is related to also to question which motivated the definition of Miller and Rock, that in fact all tried to construct there was a question of Fatih which asked if the group of area preserving homeomorphism of two disks is a simple group, and the high dimensions it was proved earlier by Fatih, and recently it was shown by then
Christopher
Gardiner and Vincent Homiliers of Consilpadini that in fact it's not simple, and this group of Hamiltonian homeomorphism of Owen Muller is a candidate for such normal, non-trivial normal subgroup, and they proved that it is a normal subgroup and it does not coincide with all error-preserving homeomorphism. But later work, as far as I know, it's about preservation of Calabi. That Calabi homeomorphism can be extended to this group, and this was also part of approach of for disproving this conjecture of fatigue. So I believe that you should ask these guys, and it's really related, I think.
Thank you.
More questions?
About this construction, if I understood correctly, in the first step, you don't touch the neighborhoods of the critical points,
Yes.
right? And then you separately sort of modify to connect the lines you created between the neighborhoods to connect them to the points, right? So on which point you're using the quantitative H principle?
So it uses, so I want to construct an invariant curve.
Right.
Connecting to critical point. And as a first step, we can construct an invariant sequence going to both sides, which here connects to one, converges to one critical point and here to another. We can do it by perturbations, but now we can, after having the sequence, we can continue and construct the curve. So we can start with more or less standard curves that connect this point, and we map this curve, look at the image, and it's C0 closed curve, and we try to map this one to and we apply this also. We have a sequence of these maps. We have infinite composition.
This is kind of like, oh, excuse me, didn't finish. So, so you just kind of a continuation of this S4 question. Suppose we just have a local question. Suppose we have a ball, symplectic ball with a structure. Does it have positive volume?
A symplectic ball.
I have a ball with continuous symplectic structure. Is it volume positive?
Yeah, volume is well defined.
Volume is well. For instance, can you like, so suppose you have this like symplectic structure on the boundary of the ball, smooth symplectic structure, and this if you compute this by Stokes theorem kind of potential, it's negative. Do we know that it's not extendable to continuous symplectic structure?
I don't know, so I have to think.
Okay.
More questions? Okay, thank you very much.